that we're going to discuss today is very rapid ionic transport. In solid. Well, when we say very rapid, it's really, really rapid, okay? Unusually high ionic conductivity. And this high ionic conductivity, if it happens in the mixed electrolyte, mixed conductors, then probably we can use this material as a cathode. Okay, but it's just an ionic conductor. Then we can use this electrolyte. Okay. Now, we have some observations of this very rapid ionic transport in solids, which is silver conducting ternary silver iodides. Iodides, we have an I there. And that has been by Bradley and Green, 1966, 1967, and Owens and Argue, 1967 and 1970. So these findings make the research on very rapid ionic transport started, okay? And also we have alkali metal, beta alumina family. Alkali metal conducting in a beta alumina family very fast, okay? And then this has been done by Yao and Kumar, 1967, and Razilovsky in 1969. So it's just around 1960, late 1960s, and this very fast ionic conductor has been studied in the late 60s, 1960s. Now, as we have discussed, we are going to have disorders, Seung-ki, disorders, ionic transport mainly by the motion of vacancies. And it applies for the alkali halides. And the Seung-ki disorder is, since the vacancies are the main defects that shows the ionic conductivity, it should be relatively low ionic conductivity. Okay, the motion of the vacancies is relatively low, and high activation enthalpies. So, Seung-ki disorder materials, even if it can belong to the fast ionic conductors. Among the fast ionic conductors, the materials with a Seung-ki disorder shows a relatively low conductivity, high enthalpy, because the transport is done by the vacancy motion. On the other hand, if you look into the Frankel disorder, silver copper halides. These materials show the Frankel disorder and ionic transport by the motion of interstitial species. So the interstitial species, so it should show relatively high conductivity and low enthalpies. Okay, so fast ionic conductors should have a Frankel disorder rather than the Seung-ki disorder. We have another categories. We can set fast, really fast ionic conductors, or sometimes it's called the super ionic conductors. And this is extremely high conductivity and unusually low enthalpies. And this unusually fast superionic conductors is mainly related to the crystal structure. crystal structure. Means this Frankel disorder or the Schottky disorder, those are the defects. It's related to the defect which is included in the transport mechanism. But in a fast ionic conductor or the super ionic conductors, it has a special crystal structure to show this unusually high conductivity. It's nothing. It is not really related to the defects that the materials have. Rather, it is related to the crystal structure itself to show the superionic conductors, like tunnel structures, layered structures, and things like that. Okay. So, in any sense, the interstitial species are important in a rapid ionic transport. We can distinguish three interstitials possible in the materials. And those three kinds of interstitials. Okay. Normal, intrinsic, interstitial. That is an example of NaCl structure, and you have a chlorine ions, all the face center, the cubic lattice, and then or quarter offset place you're going to have. Okay. You're going to have an Na structure. So you may think this sodium ions is in the interstitials, consisting two FCCs overlapped and offsetted by quarter. So octahedral site of Cl minus, the sodium ions occupy octahedral site of Cl minus. And in this case, the sodium, it has a fast ionic conducting species in this NaCl structures, and we call that intrinsic interstitials. And disordered interstitial. And there is inherent disordered material in the anion close-packed structure, like anion close-packed structure. Cation disordering. cation disordering in, say, in anion close spectral structure. And another interstitials that we have to think in our fast ionic conductors is the external interstitials, say, external interstitials is related to the open structure, like a layered structure or the tunnel structure. Okay. Typical example of layered structure is beta alumina. Beta alumina. And the tunnel structure is a potassium tungsten, potassium hexatungstate. For example. Okay. By the way, the potassium hexatungstate is the material that I used for my PhD thesis in Stanford University. Okay. And this external interstitials, very high mobility of fluorine interstitials at room temperature. Example, lithium in potassium hexatungstate. WO3 point. And the diffusion coefficient, lithium in the potassium hexatungstate is about 10 to the minus 7 centimeters square. 10 to the minus 7 centimeters square per sec. This is a diffusion coefficient, okay, at room temperature. This is a very high value as a diffusion coefficient in a solid state. Normally at room temperature the diffusion coefficient is about 10 to the minus 16 to 10 to minus 19. So this is a very high diffusion coefficient, we can say, is 10 to minus 7. So we do have a theoretical approach to understand why these materials show superionic conducting. How we can understand the superionic conductivity in these materials. Okay, and the first model that we have to start is the simple single jump model, which is listed on the text that I handed out. So that is simple single jump model. Okay. When you say ionic conducting, by definition of ionic conducting. Okay, should be the electrical charge transport by ionic motion. So usually the electrons and holes, the electric carriers, they are moving very much faster than the ions. But in the electrochemistry, the electrical charge transport controlled by the ionic motion. That's what we can say, because ionic motion is very much sluggish compared to the electrons' motions and things like that. Okay, and since Warburg, this guy is very famous, Warburg impedance that we have discussed in the HC impedance spectrums. In 1884, recognized the transference number. Transference number is the total number of a movement of the charge transport, and the ratio, the charge transport is done by the ions or the electrons. Those ratio is called transference number. Okay, and that transference number is important in superionic conductors. And the Frankel disorder is important that we have just mentioned. Okay, Frankel disorder is the vacancy and the interstitials, and especially this interstitial is important. Is more important than Seung-ki disorder, where the vacancy is important. In this case, the vacancy, and then this pair, the vacancy pair, is important. Now, before we go into the single jump model, let me just give you the numbers that we are talking about in fast ionic conductors. How fast we are talking about? The highest value of ionic conductivity in a solid. Okay, at room temperature. That is rubidium, silver iodide, rubidium, silver iodide. Wow, this is really weird materials. Whoever invented those materials. And that has been measured by Owens and Argue in 1969. And that has been shown you a minute ago. And it turns out to be 0.3 ohm centimeter at room temperature. Wow, this is an amazing number. Okay, this is even faster than that of alkali halides. By 10 to the 14th. God, it's really fast, right? And this means we need new insight for understanding of ionic transport phenomena. We need a new insight. This abnormally high, and then it cannot be explained in a general manner. Okay, so there must be something in the materials which shows this super ionic conductions. Okay, so we developed the simple model and that has been tried by Richard. No, not Richard, Rickard. Rickard. 1973. And this simple model try to find out the maximum value and fix the lattice. Okay, so it's just a simple theory. The thermal velocity V, okay, and without oscillation means it moves but never come back. Okay, we suppose no without the oscillation at each side. The lattice point. And jump frequency let's say nu is just v velocity and the distance between the jump. And let's suppose distance of a jump like 1 angstrom, okay, at 300 degrees centigrade. It's not the room temperature. We just calculate the frequency turn out to be 3.4 times 10 to the 12 per second. And we know the diffusion coefficient is alpha d square over nu, and alpha is equal to 1/6 for cubic. The geometric factor alpha is 1/6 for the cubic. Then if we apply the nu, the jump frequencies, just to get from there, diffusion coefficient turn out to be 5.6 times 10 to the minus 5 centimeters square per sec. Okay? Now, this is this experimental value that the silver iodide case using the Nernst-Einstein relations. We can get the theoretical conductivity at 2.8 per ohm centimeter from here. Okay? And experimental value, the conductivity is 1.97 per ohm centimeter at 300 degrees centigrade. And that has been measured by Vist and Josephson in 1969. So what does that mean? The theoretical value we can have, the conductivity, is a 2.8. In the real sample, we had this much close values to this theoretical value. But the important thing is, in these theoretical values, we have almost impossible assumptions in here. Like in this simple jump model, what we have assumed this means all silver ions are free to move. And every jump attempt is successful. As the assumption of simple limiting model. So all silver ions are free to move. That is almost impossible thing to happen, and every jump attempt is successful. With these incredible assumptions, we have conductivity of silver in silver iodide has turned out to be, it calculated to be 2.8. But in experimentally at 300 degrees centigrade, the actual numbers that we have is that high, that close. So this means actually in this silver iodide at 300 degrees centigrade, actually this thing is happening, right? So there should be a reason behind this why we have why this almost impossible thing can happen in the silver iodide. Why it happens? What is the crystal structure at 300 degrees centigrade to make this thing happen? Things like that. Okay. Even higher conductivity has been observed by the Chu et al. 1973, and this guy is my senior in Stanford University in my lab. Okay. In 1973, silver diffusion coefficient in alpha silver sulfate at 200 degrees centigrade is about 0.47 centimeters cubed per sec. Okay, that is a lower value than that, but look at the temperature. The temperature is 100 degrees centigrade is lower, so this conductivity is amazing. And moreover, this alpha silver iodide is a mixed conductor. So it can be used as a cathode materials. And in his thesis, PhD thesis, he claims that this abnormally high conductivity can come from the fact that since it's a mixed conductor, the electron movement has to be associated with this ionic transport. Large thermodynamic enhancement factor in this mixed conductor is by interaction of electrons and ions in diffusion. Okay, and several orders of magnitude larger than the theoretical values from simple limiting model. So in the handouts, there is an introduction of the superionic conductors. Like in the plot, you just refer to the handouts that I have given you, the KCl and AgCl, and we have some values for the beta alumina, and then we have some values which is moving in between silver iodide, something like that. You can see the plot in the handout. Okay, this is 1,000 over T. This is a low temperature and high temperature, right? And low temperature means room temperature. High temperature means not exceeding 500 degrees centigrade. If you have a measurement the temperature more than 500 degrees centigrade, it is not realistic anymore. You never run the battery at the temperature more than 500 degrees centigrade. In any sense, it doesn't have any meaning if you take the temperature more than 500. Okay. So you can see the beta alumina shows relatively high ionic conductivity all over the temperature range. Here, the KCl is alkali halides. And the Seung-ki disorder material. Okay? And AgCl, which shows higher than the KCl, AgCl is a Frankel disorder material. And sodium beta alumina, where the stoichiometry M aluminum 11O17, something like that, and M is the metals like a sodium and other metals. And the AgI is a fast ionic conductor. That sodium beta alumina is layered materials. So, in summary, fast ionic conductors. Okay. Number one, conductivity is unusually high. Number two, small temperature dependence of conductivity. Okay, activation energy for the conduction is about 2 to 5 kilocalories per mole, and this is low entropy of motion, very large concentration of mobile carriers, and very small sigma naught values, okay, which is related to the frequencies, the vibrations. And that is 10 to the 3 ohm centimeter. Okay. This means low value of attempt frequencies. Small entropy of motion. So for 1 to 3, we come to a conclusion that something very strange, we should say something very strange, happening in the superionic conductors. Okay? And we really don't know what is the what's happening, which is called the strange in the superionic conductor. But in the next week on Monday, we'll try to understand what's happening in the superionic conductors by putting some parameters in the simple hopping model that we have discussed, so that we have real figures, numbers, and then we're going to review the materials exhibit the fast ionic motions, and then we're going to wrap up the lectures in this semester. Okay, any questions?